Assalamu alaikum and welcome to another session for EEE 6311. So today what we are going to show, basically in the last class, as I told that we actually incorporated the transmission loss into our economic load dispatch model. So the transmission loss, let's say, was defined by PL. That was the total transmission loss of a system. And we incorporated this PL with the original system demand PD, and we found that the total generation I equals 1 up to n number of generator PG, that should be exactly balanced by the load P demand and the loss occurring throughout the whole transmission network. So that is to say that this model is applicable, this equality constraint is applicable for those systems, for those power systems where there is significant length of transmission line. So significant length of transmission network is available or is present. So because of this length of the transmission network, we cannot ignore the transmission line RL, that is the resistance of the transmission line, as well as the inductive reactance of the transmission line. And accordingly, we have to consider the losses occurring in these components. So because in the economic load dispatch problem, we are not too much bothered about the reactive power balance or reactive power optimization. Our main focus here was the real power loss that is occurring on the resistive part of the transmission line. So I square RL, that is the power loss that we generally represent by. And if I consider the three-phase loss, then we simply multiply it with 3I square RL. So this is more or less the representation, generic representation for transmission line loss. However, as we suggested in the last class, the last physical class, that our target is to minimize the generation cost. So here, what we did, basically, we replaced this whole expression of transmission loss by the help of some equivalent representation, and that was simply some function of PGIs. Okay, so in today's class, what I will try to do is to establish this relationship between this representation of I square RL kind of loss and the corresponding representation of the losses represented as a function of the generation of each generating unit present in the system. So that is our target. So let's start then. So to start with, we assume that, let's say it's a two generator system. Okay, just a simplified model, two generator system. And each generator is actually generating some current, which is, let's say, denoted by the first generator is generating some current IG1, and that is being fed into a network. So this is basically our transmission network. And of course, in the transmission network itself, there are many number of buses as well as many number of interconnections or the links between the buses, which are usually known as the lines, transmission lines. And ultimately, at the receiving end, we have a series of loads connected at different buses in the system. So we will assume that combinedly the load is consuming ID amount of current, and there are two generators. So the second generator is, let's say, represented by the second generator current output is represented by IG2, And these are the switches, let's say. So this is IG2, and we simply choose one of the links among all the available transmission lines in our system. So let's say this is the pth transmission link carrying current IP for the time being, for satisfying the demanded current ID. So this is a two generator system, and what we will do initially, we will first set generator 1 on. So this switch is on. So what we will say now, that when generator 1 is on, so let's say this is case number A, gen 1 is on, or simply that is to say that there's only one source is active, the other source is inactive. So in that case, the current that is flowing through this transmission link, the pth transmission link, is, let's say, IP1. Okay. Case B, in the case B, what we will do, we will simply do the reverse. So that is to say now that IG1 becomes inactive. So the switch becomes open. IG2 on the other hand becomes active. So this is our IG2. We have the same transmission network. So this is, let's say, case B. And that pth link, now due to the source 2 being active, the current flowing through this pth link is, let's say, IP2, whereas the total demand is still ID. So remember, the link that we are actually choosing, this is only one of the links actually present or actually available among many links present in the system. Okay, so there are many such links available within the transmission network, and we are choosing only one of the transmission links. So there are maybe 1, 2, 3, up to n number of links or transmission lines, and P is one of those, only one of those. So that means, well, if we are trying to satisfy this demand ID here with the generating source IG2, simply it is quite simple or quite easy to see that only one source is available. So whatever number of links or interconnected links are present inside, the final demand ID, demanded current ID, and the initial source current here should be exactly equal. Remember, this is the total current. So we can simply write IG2 is actually ID. And remember, all these are phasors. That's another point I missed. All these are actually phasors. So this is AC transmission network and AC system. So all these are phasors. That means each of them has their own magnitude as well as some phasor angle. So IG2 is equals to ID in this case. And in this case, IG1 is equals to ID. So now, how much, what is the proportion of current? So among the whole current IG1, what is the proportion of current that is being carried by the pth link, pth transmission link in this case? And at the same time, among these IP2 amount of current, okay, IP2 current. So this is actually some portion of my actual source current. Okay, this is some portion of my actual source current actually. So what is the proportion? Let's say the proportion here in this case, we represent the proportion MP1, that is nothing but the proportion of current being carried by the pth link IP1 divided by the total current IG. And because this relation is true, so we can also write actually in this case, specific case, IP1 by ID. Similarly, we can write that the proportion of current that is being taken by this pth link from the total current IG1 can be written as IP2 by IG2. And again, because this is true, so we can also write it like IP2 over ID. Okay. So these MP1 and MP1 and MP2, these are nothing but we can term it like the current distribution factor. Okay, current distribution factors. Now the question is in general, because you have two generating units available, so it is quite logical to say that, well, both of these generating units should be turned on at the same time to satisfy the demand. So we can simply go for now superposition. Okay, so we did it for source 1 in case A, we did it for source 2 in case B. Now we want to see case C, where we will turn on both of these sources. So in case C, what we will do is simply this. So both of the sources will be turned on. This is IG1 being turned on. This is IG2 also turned on. This is the link, the pth link. Now this is IP and this is the demand, the combined demand ID. This is case number C. So now, so okay, missed it. So this is generator 2 is on here. Now here both, in case C, both generators are on simultaneously. So because this is superposition, so simply we can say that IP here should be IP1 plus IP2. Okay, so this is the total current flowing now through the pth link. So with both generators on, we should have now IG1 plus IG2 equals to ID. Okay, so now if we continue from here on, so this is one of the relation that is true for KC. This is another relation that is true for KC. So if we continue with this, let's say where do we actually reach? So IP is IP1. So using this relation, we can write IP1 equals MP1 into IG1. Remember, these are phasors. Then we have IP2. IP2 is MP2 into IG2. And now let's say if we want to express both IG1 and IG2 by their corresponding magnitudes, IG1 angle sigma 1 and IG2, so let's say angle sigma 2. So this is what we can get if we take some phasor representation, like some magnitude of IG1 and IG2 and the corresponding phase angles sigma 1 and sigma 2. So if we use the Euler's identity, then clearly we can again go further, a bit further, like IG1 could be now expressed as, okay, let me erase some part of it. So we can represent this IG1 and IG2, okay, with the help of the Euler's identity, which says that, well, if you have some phasor representation, then that phasor representation could easily be replaced by the corresponding sine and cosine components. That is the Euler's identity. So that is to say, if we leave this, so we have this IP. If we continue from here, so let's write it here. IG1 is simply IG1 absolute. Then you have cosine sigma 1 plus j sine sigma 1. Similarly, IG2 phasor is IG2 multiplied by cosine sigma 2 plus j sine sigma 2. So this is what we have. So we can get rid of this. Now we have IP is MP1 IG1 plus MP2 IG2. So let's see, let's say what we do here. So we continue with IP, that is MP1 IG1 cosine sigma 1 plus j sine sigma 1. So this is cosine sigma 1 plus MP2 IG2. So that is IG2 phasor. So magnitude of IG2 multiplied by cosine sigma 2 plus j sine sigma 2. So we can also get rid of this. Can also get rid of this. Now, what we can do is simply we can take out the real part and imaginary parts. So this is cosine sigma 1 plus MP2 IG2 cosine sigma 2. Let's put it into a bracket plus j MP1 IG1 magnitude sine sigma 1 plus MP2 IG2 sine sigma 2. So now if, let's say, instead of expressing this IP in terms of phasor, if anyone is interested in finding the absolute value of this, so what should we do? We have simply a real part and an imaginary part. So we can simply write it like this. So we can write it like IP squared, so that we can get rid of the square root. So I mean, in general, if you have any phasor, okay, if any phasor is a plus jb, let's say if this is phasor x, then x absolute is a square plus b square. So what I am saying is this x squared should be a square plus b square. So I don't want this square root. I simply want a term without the square root. So I just need to make the square of this absolute value. So this is what I'm doing here. So simply what you have to do, a square plus b squared. So this is my b and this is my a. So simply I can write MP1 IG1 cosine gamma 1 plus MP2 IG2 cosine gamma 2. So this is a squared plus b squared. So this is MP1 IG1 sine sigma 1 plus MP2 IG2 sine sigma 2 whole squared. Okay, so you can get rid of this. So we are left with simply the a square plus b square type of form. And then if we want, we can remove the bracket, we can expand these forms. So if we expand this, let's say, what do we have? So MP1 IG1 squared sine squared sigma 1 plus MP2 IG2 squared sine squared sigma 2 plus 2 MP1 MP2 IG1 IG2 cosine sigma 1 cosine sigma 2. Okay, so this is what we have for this first part. And then for the second part, we have MP1 IG1 squared sine squared sigma 1 MP2 IG2 squared sine squared sigma 2 plus 2 MP1 MP2 IG1 IG2 sine sigma 1 sine sigma 2. So this is for the second part. So now if we look a little bit carefully, then we can identify that, let's say we have this mp1 ig1 squared cosine squared sigma 1 and mp1 ig1 squared sine squared gamma 1. So these two would actually yield mp1 ig1 squared. Okay, next what do we have? Next we have this mp2 ig2 squared cosine square gamma sigma 2 mp2 ig2 squared sine square gamma 2. So this will become mp2 ig2 absolute squared. The remaining part we have to simply take this common. So you have what is common, this and this are common in both parts of the expression. So let's take it to mp1 mp2 ig1 and ig2, and then you have cosine sigma 1 cosine sigma 2 plus sine sigma 1 multiplied by sine sigma 2. So this is something like cos A cos B plus sine A sine B. So you can write mp1 ig1 squared mp2 ig2 squared 2 mp1 mp2 ig1 ig2. Then I have cos A minus B. Okay, so this is what actually we will get for the pth branch current, magnitude and square of that. Okay, so this is the expression. Now why are we actually looking for this? That is the main question. Why are we interested on this? The main reason for that will be clear. Just wait a few seconds. So we have got some I squared term. Remember the loss in a line, the loss in a transmission line can be represented by I square R. So we have got an expression of, let's say, so the current is flowing through the pth branch. This is the pth branch or the pth link, whatever you say. This is our pth branch in the transmission network. So I have got an expression for the absolute value of the current flowing through the pth branch and the square of that. So this is that expression. So now we know that for the total current, if I have, let's say, k number of branch or n number of branch, whatever, so I have to add up all these losses. Okay, all these losses. So and then for three phase power, this will be like 3 I k squared r k summation of I equals 1 up to, let's say, n, or let's make it, it's not k, it's actually p, because we are looking for the pth branch. So this is for the pth branch. Just a minute. So this is ip square rp. Of course there will be the absolute sign. So this is actually the total loss, pl. If I have n number of branches in my system, then I have to add up all those losses, and because of the three-phase system, there will be the multiplication of 3. So this is for one of the phases. I square r is for one phase. For three phase, it is 3 I square r. For n number of branches, this is the summation. So this is the explanation of all this over here. So this is why actually we targeted to get this IP absolute squared. Once you get that, then you see the remaining part is quite easy to calculate. To reach at PL, the remaining part is quite simple. Simply you have to multiply by RP and you have to take the summation for all the branches. So this is what we did. So now the PL is simply, you can write that summation I equals 1 up to number of branches. Let's say the number of branches n again. So 3, and then I have to take the whole expression over here. So let's put it inside the third bracket, mp1 ig1 squared plus mp2 ig2 squared plus 2 mp1 mp2 ig1 ig2 cosine sigma 1 minus sigma 2 into the whole thing multiplied by rp. So that is the expression of PL. Now let's try to simplify it a little bit more. Remember, our target is not yet achieved because we actually want to express PL as some function of PGIs. Okay, that target is not yet achieved, but we are almost there. So to reach here, what the next relationship that we would like to use at this point of this derivation is simply this. We all know that IG in general is PG. So if I make it like IGI, so it should be PGI divided by square root of 3 VL. I can put it I here. V line into cosine theta I, where cosine theta is the corresponding power factor for this specific generator, ith generator. Okay. So if we can do that, then you can clearly see that now instead of IG, we can bring the PG over here. And that is the target, bring the PG here. So let's do it. I equals 1 up to n, 3 summation 3 mp1. Then I have, this is IG1, so this would be PG1 squared, square root of 3 VL1 cosine theta 1 plus mp2 pg2 squared root 3 VL2 cosine theta 2 plus 2 mp1 mp2 we have IG1 and IG2, so it will be like PG1 PG2 divided by, we have 3 square root of 3 here and square root of 3 there, so it will be 3. Okay, probably I have done a little mistake here because there is IG1 squared, so this should be VL squared cosine squared theta 1. Similarly here it should be 3 VL2 squared cosine squared theta 2. Then here I have IG1 and IG2. So PG1, PG2, 3 VL1, VL2, cosine theta 1, cosine theta 2, multiplied by RP. And of course, I have this cosine sigma 1 minus sigma 2. I think it is okay now. And then what we will do, we will try to represent this PL in the generic form. So now our next target is simply, you can clearly see that this 3 is cancelled from everywhere. So we don't have to bother about the 3 term, it's already cancelled. So what is left is, actually we can say we have some PG1 squared multiplied. So let's put it inside the bracket. We have some MP1 then VL1 squared VL1 squared then cosine squared theta 1 plus you have some PG1 PG2 form type of thing, cosine sigma 1 minus sigma 2, and then VL1 VL2 cosine theta 1 cosine theta 2 MP1 MP2 into 2 plus PG2 squared MP2 divided by VL2 squared cosine squared theta 2 divided by RP. Okay, so so this thing is actually, you can say I equals 1 to n. So now we can write it like PG1 squared, and this whole thing over here, we call it B11 plus PG1 PG2 cosine sigma 1, okay, PG1 PG2, sorry. So it will be again, the whole thing will be B12 plus PG2 squared B22 into RP. So now, okay, so we are going to introduce the B coefficients, and probably the little correction. Okay, let me erase this. Little correction is here. So the B coefficients would be not exactly this encircled part, but a little bigger part. So let me write it in terms of B coefficients like this. So PG1 squared B11 plus 2 PG1 PG2 B12 plus PG2 squared B22. So if this is my targeted expression for PL, then I can compare this line and this line, and I can simply find out what are my B coefficients. So then if we compare it, what we get is simply this: I equals 1 up to n. Remember, this I equals to 1 up to n is actually the number of lines. So here I have only RP. Okay, I have only RP, so I have to take all the line summations here. I have to include all of those effects there. So actually P is one of those. Okay, P is an element of this n. So P is an element of n. So then what is B11? So let's go back to B11, summation of I equals 1 up to n. So it is PG1 squared B11. So the remaining thing, whatever is remaining other than PG1 squared, should come here. So VL1 squared cosine squared theta 1. And of course, you have to remember that these VL1, VL2 all are actually the magnitudes of the line voltages. These are not the phasors, these are the magnitude of the line voltages. So VL1 is squared cosine squared theta 1. Then B22 is again simply, okay, multiplied by RP, of course. I equals 1 up to n MP2 RP. This is MP2 VL2 squared cosine squared theta 2. And then the middle one is B12. So that is a little larger part, longer compared to the others. 1 to n cosine. Okay, let me put the cosine later on. We start with MP1 MP2 divided by VL1 VL2. All these are magnitudes, remember. Cosine theta 1 cosine theta 2 cosine sigma 1 minus sigma 2 and multiplied by RP. So these are my beta coefficients or B coefficients. And in general, this expression is actually known as the power loss power loss expressed in terms of beta or B coefficients. Okay, so there are some remarks actually on this derivation. Actually, the derivation that we have shown here is only for 2 machines. So for 3 machines, the derivation would be something like this. Okay, it would be something like this. So it would be like PG1 squared B11 plus PG2 squared B22 plus PG3 squared B33 plus 2 PG1 PG2 B12 plus 2 PG1 PG2 B23 plus 2 PG1 PG3 PG1 PG3 PG1 PG3 B13 or B31. So that would be for 3 machine system, and in the same manner we can easily get the generalized form. Okay, for n number of machines, or let's say ng number of generators, what would be the expressions for this power loss, power transmission power loss expression. Okay, so that's it for today. So this lecture is actually taken from the book of the Nagrath Kothari. They are the authors. It is not available in your textbook. The textbook version is a little bit more complex than this, so I thought it would be easier for us to go with the easier version. Okay, so go to the Nagrath Kothari book and you will easily find this topic there. That is the in the chapter of optimal power dispatch chapter, you will get this detailed derivation for the PL that I have shown here. So now that we have got the expression for PL, and actually in the last class I solved one example having the expression of PL represented a little differently. Of course, in that expression actually we had 3 generators, but we actually ignored the effect of this B12. All the cross couplings were actually ignored. So the expression was simply that was composed of the first 3 parts over here. Okay, so that's why it was mentioned as some simplified expression for the transmission power loss in a network. But however, this is the more general one, more elaborate one. So I hope you will go through this again in your home, and if you have any question, you can ask it in the next class that we meet inshallah next Friday. Okay, assalamu alaikum.